Okay, so good afternoon, everyone. So this week we continue to study the course of smart system in automation. Okay, and I hope all of you have already registered the course project. Okay, so if some students haven't registered the course project, please contact Miss Tom, digital assistant. She will have you to add your name and your teammates' names into the Google Excel. Okay. Ừm, được. Ờ, nhưng mà không khuyến khích. Okay. Okay, I will share my screen to all of you. Okay. So actually, I just limit the maximum number of students per group. Okay, and of course, you can do the course project for yourself. Okay, but it is not encouraged by me because a lot of work, a lot of task you need to complete when you do the course project. Okay, so if you have uh, more group members, okay, it is better for you because sometimes you have some difficulties. Okay, you have some problems and you can discuss what with your teammate before you ask me. Okay, so of course, yeah, you can do that for yourself, but remember that. Okay, it's enough encouragement. Okay, so up to now we have 12 groups. Okay, and of course we have some groups with two students. I think that's okay. And yeah, I am a little bit busy, so I try to give the topics to you. Okay, this week. Yeah. And of course, as mentioned before, okay, I mentioned last week, okay, when you receive the topics, okay, you need to read the papers, okay, you need to read the topics and then repeat the work from the topics. After that, you can choose um, one algorithms from the list. Okay, here I will give you the list of optimization algorithms. Okay, yeah, and then you can pick up one of them. After that, you can compare the result. Okay, the simulation result from the topics and the simulation result from the algorithms that you select. Okay, and then you give some discussion, some comparisons, okay, some analysis about the result, and add your discussion into the final report. Of course, we have some classes, okay, to help you, yeah, okay, to help you clarify, to help you solve some problems. Okay, so the maximum is 5 classes. Okay, here, yeah, and I will come to the classroom. Okay, I will come to the classroom and you can ask me if you have any problems or any difficulties about your project. Okay, remember that you need to make the progress report. Okay, to let me know what problem you have. Okay, what kind of difficulties you have, and I will suggest you how to solve the problems. So um, if you don't report to me, and then I don't know for what kind of difficulties you have. And then when you make the presentations, okay, you cannot solve the problem. Of course, you get 0%. Okay, remember that you have 5 classes, okay, to get my suggestions. okay, to your topics. Yeah, remember that. Okay, here we have totally 5 classes. Okay, 2nd January, 9th, 16th, 23, and 30. Okay, yeah, so you have 1 month, at least 1 month to do the project. Of course, now maybe this week you receive a topic. Okay, you can discuss with your teammate how to do it. Okay, how to write the MATLAB program, how to understand the objective function, blah blah blah. Of course, I also give you some tutorials during the class. Okay, the 1 or 2 tutorials. After that, you can understand the objective function. Okay, yeah, and you do the project. Any questions so far? Um, the timeline is over. Okay, yeah. So now you cannot register anymore, but you can send email to me, and I will ask Miss Tom to add. Okay, to add your name into this Google Excel. Okay, the deadline now was already over. Okay, yeah. And now you cannot change. Yeah, you cannot change. I mean, you cannot swap one group to another group. No. Okay, this is fixed. Okay, because you have more time to find your roommate. Okay, and then you register for yourself, and now you cannot change anymore. Okay, you need to follow the list of groups here. Okay. So when I assign the topics to you, that means you cannot register anymore. You cannot modify anymore. Okay. So when you receive the topics, that means I will close the registration. Okay. And yeah, you cannot. Sorry. And then you cannot register as anymore. Okay. And okay, here I also give you some reference about the rating. Okay, so totally we have 120% max. Okay, of course you just need 50%. Okay, to pass this course. So for the presentation, is occupied 25%. We have presentation slides, fluency, time management, Q&A, and some demonstration. That means you run the code. Okay, you show me some simulation result. Okay, yeah, and you get max 25%. For technical report, okay, about the content, 10%. For format with figure, tables, formulas, blah, blah, 5%. And results, analysis, and discussion is occupied 10%. Okay, so you already studied technical writing, right? So you have some basic skills how to write the final report. Okay, we have introduction, we have literature reviews, we have implementations, okay, results, analysis, and discussion, blah, blah, blah. Okay, so of course you understand how to apply the knowledge from technical writing courses into the final reports of this course. Okay, homework 20%. Okay, and remember you need to submit your homework on time. If you have a late submissions, you get 0%. Okay, because I give you the deadline. You know, deadline is very very convenient for you, right? Yeah, when we finish the lectures, we have at least 1 week or 2 weeks to complete the homework and submit the homework into the VGU Moodle. Okay, so remember that if you have the late submissions, okay, you get 0%. And for the final exams, Okay, the final exam will be 50%. Yeah, we mentioned before from lecture 0 introduction of this course. And for the final exams, the content of final exam will be relevant to the course project. So if you don't complete the course project, that means I mean it's not easy for you to do very well the final exam. Remember that we have the relevance between course projects and final exam. So if you complete the course project very well, I believe you can get the a good result of final exams. Okay, and you can see the final score here. Okay, and yeah, of course, I hope you can pass this course. Okay, all of them will pass this course. Okay, so the easiest way to pass this course is to complete the course project, because the course project occupies 50%. Okay. Any questions so far? Are there any questions from the classroom? Are there any questions from the classroom? Okay, yeah. So for now we continue to study lecture 2, and we hope we can finish lecture 2 today, and we move to lecture 3. Oh, I forgot to, I forget to upload the PDF files of lecture 3 into the VGG Moodle. So later on, I will upload it. Okay. So now we come back to lecture 2. Yeah, so last week we discussed about GA with real parameters, and now we take some time, maybe 5 minutes, to review the content last week. So for GA with real parameters, we have many various crossover operators, right? And the easiest way is linear crossover. Okay, linear crossover we already discussed. Okay, yeah, we need to randomly select the parents, and then we generate the offspring of the children. Okay, and the second one is arithmetic crossover. Okay, yeah. Okay, so for linear crossover, this is the symbol crossover operators, because we have coefficients, they are constant, right? But if we consider arithmetic crossover, now the coefficients, that is 1 minus Reymers, and you need to know how to set up Raymer, right? And the next one is plane crossover, BLX inverse. So later on we have the homework with this one. Okay, so here coefficient will be changed, because here coefficient is 1 minus rho, and this one is rho. Okay, and we know the formulas how to calculate rho, right? Yeah, rho is 1 minus 2n for uniform distribution with mu is 0, and standard deviation is 1. Okay, minus n for. Okay, and for represents a constant between 0 and 1. Okay, so it is random to initialize the values of n for. Okay, then I also explained to you the boundaries of the children. Okay, yeah. So we have for BLX, right? Yeah. So we can skip linear crossover. Okay, we can skip arithmetic crossover, but for BLX, okay, BLX and for you need to consider. Okay, and we have the homework for that. And next one, sorry, sorry. The next one is SBX. SBX. So for XBX is the simulated binary crossover. Okay, so this one is very interesting. Why? Because they give us the information of beta. What is beta? Beta is quasi random factors. Okay. And how to calculate beta? It depends on NC. Okay, NC. So if we know beta, okay, you can get the coefficient, right? This is coefficient of B1. This is the coefficient of B2, and to get C1, this is coefficient to get C2. Okay, yeah. And what's the NC? Okay, so NC is dispersion factors. Okay, dispersion factors. So, of course, you need to initialize dispersion factors. Okay, dispersion factors. Yeah. So if we know NC, we can calculate beta. Okay. So if the random number is less than or equal to 0.5, okay, we calculate beta by this formula. Otherwise, if a random number is higher than 0.5, we prefer to use this formula to calculate beta. Of course, but it's quasi-random factor. Okay, and then we also some demonstration for XBX. Okay, and the next one is UNDX. Okay, UNDX, we say is unimodal distributed operators. Okay, yeah. So now we have B of we have B of X, and first we have SBX, and we have now UNDX. Okay, yeah. So UNDX a little bit complicated because we need to choose more than two parents. Okay, you need to choose more than two parents just to generate these children, the offspring. And I also discussed with you how to calculate D. Okay, the orthogonals D. Okay. Yeah, and we have many steps. Yeah, we just follow the steps. Step one, we calculate the mean parent. Okay, so the mean parents is calculated by two parents. Okay, two parents from mu parent. Okay, yeah. For example, here we have three parents. We just pick up for two of three, and then you can get the mean parent. This is step one. Step two, we need to calculate the direction vectors di. Okay, so di is bi minus b. Okay, bi is the parents. Okay, the parent I minus the mean parent, you can get di. Of course, this is vector. This is vector, so di is also the vectors, and we say di is the direction vector. Step three. Step three, we need to calculate AI. Okay, AI. So for AI is the ratio of di over the length of di. Okay, here we see the length of di and the magnitude of di. Okay, yeah. So this one like normalization, right? Normalization. So if you study linear algebra, you can know for AI that means normalization of di. Okay, and step four. Now we know from EI. Okay, and next step we calculate D. Okay, It depends on the parent you choose. Okay, yeah. So if you choose the parents B3 and B1, sorry, B2, yeah, B1 and B3, sorry. Okay, yes, okay. Okay, so if you choose the parents B1 and B2, so here must be B3. Okay, or you can say that we consider here, okay, this is the difference between B2 and B1, okay, and the other this is B3, B3, B3. So if we have B1, B3 and B1, okay, so here is the difference between B3 and B1, and here's B2, here's B2. Okay, and similarly, you get this one. Okay, I also mentioned to you before. Okay, so for then, yeah, we can simulate the distribution of offsprings. Okay, after that, we can calculate CI. Okay, CI. What does it mean? CI? This is children. This is children. Okay. For example, if I would like to calculate C1, we have a mean. Okay. And here we have J is 1 and mu is -1 and mu is 3. So you get J is 1 to 2. Okay, because 3 is -1, you get 2. Okay, so here you get this one, right? We have N0 sigma 1 square dj ej. Okay, yeah. Yeah, this is the general formulas, right? And then plus normal distribution with mu of 0 and variance sigma 2 square, sigma 2 square. Okay, d e and mu. Okay, and mu e3, so this is d e3. Okay, so we can calculate sigma 1 by this one, right? These formulas and sigma 2 by this one. Okay, so because this is in the sum of this term, so if j is 1, you can get this one, and j is 2, we can get this one. Okay, and now you can get d. Okay, e3. Okay, so we know how to calculate e1, right? e2 and e3. Okay, we know how to calculate d. Okay, and this is the length of d. Okay, d1 e1 and d2 e2. Okay, yeah. After that, we have this MATLAB demonstration. Okay, remember here we calculate the mean parents according to parent 1 and parent 2. Of course, we have 3 parents, but when we calculate mean, we only consider 2 parents, B1 and B2. We take the average. Okay, you can get mean. Yeah. So if here is B1 and B2, so remember that here. I mentioned before, right? We take the difference between B1 and B2, and the others will be B3 minus B1, blah, 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 like this, like this. Okay, yeah. And yeah, I also explained to you, right? Okay, yeah. So this is the norm, right? This is the norm. Norm, that means the length, right? B2 minus B1. Okay, it's similar to B1 minus B2 because we calculate norm. Yeah. So here you have the calculation of d. Okay, based on this one, d. Okay, yeah, and yeah, of course we get some solution. Okay, it depends on how many iterations we have. Okay, and then you can observe the distribution of the solutions. Okay, any questions so far? Just help you to review. Okay. So if you have any questions, you can ask me, or you can ask Miss Tom, and then Miss Tom will repeat to me. Okay, so for now, we have B, L, X answer. we have SPX, okay, we have UNDX, and now we have the last ones, right? The latest one, okay, this is BCX, okay, BCX. So for BCX, step one, we also calculate the mean. Okay, the mean parents. But remember that now, the mean parents is calculated by own parents. Okay, so if we have three parents, we have B1 plus B2, okay, plus B3 over 3. Okay, yeah. Or we can say that we have 1 over 3, the sum of I is 1, 2, and mu. And mu is the number of parents for the population. Okay, this is step one. Step two, we also calculate DI. And step 3, we calculate EI. So, okay, so steps 2 and step 3 will be similar to the step of UNDX. Okay, yeah. Next one, now we calculate orthogonal distance, okay, sigma. Sorry, delta. Okay, we need to calculate delta J. So when you get delta J, you can get delta average. Okay, yeah, so this formula to have us to calculate the delta average. But how can we calculate delta J? Okay, we know before, right? We know before. So for example, if we would like to calculate delta 2, delta 2 means D2. Okay, yeah. So here you take B2 out, right? And you replace B2 by B for bar. Okay, you can get C2. And then if we calculate delta 1 or D1, you just pick off B1. Okay, this D1, right? D1, yeah. So you just let B1 out and replace by B average. Okay, and now here should be B2 minus B3 minus B2. This is blah blah blah. Okay, that means we skip B1, parent 1, and now for delta 3, the same. You know, we skip parent 3, and then we can calculate D3. Okay, so if you don't remember, just rewatch my recording. Okay, you can understand now. Just review. Okay, yeah, and remember that when we calculate this term, you should make sure you should make sure J different from I. Okay, J different from I. For example, here is BI. Okay, so if here is B1, okay, here must be plus and 0 sigma 1 square. Okay, what else? D1, right? D1 plus. Now, J different from I, and I is 1. So now we can get J is 2 to 3 because J different 1, right? J different 1. J different I, and I is 1. And then we have a normal 0 sigma 2 square, delta average, and then EJ. Okay, yeah. So like this, you know, you get the B1, okay, and this is what, right? And here you can get N0 sigma 2 square delta E2, and this is E3. Okay, so the key was is delta average. Delta average is here. Okay, delta average. Okay, yeah, delta average. So delta average is J different from I. That means we calculate the delta 1, delta 2, delta 3, and then you divide this by 2, you can get delta average. Okay. So when we remember that it depends on the I. You know, if I is 1. If I is 1, so here we just consider delta 2 and delta 3. Okay, so if I is 2, now delta 1 and delta 3. If I is 3, here we have delta 1 and delta 2. Okay, remember that. So for now, we have MATLAB code, right? Okay, so this is step 1. Yeah, step 1. We calculate the mean the mean parent, or we say the parent central point. Okay, after that we calculate direction vectors. We calculate direction cosine. That means E1, right? EI, EDI over magnitude of DI. Okay. Yeah, so you can get E1, E2, E3. Okay. And then now we consider how many parents we have n mu E3. We have B1, B2, and B3. So now we would like to get the children. Okay, so if the selected parents is 1, if n is 1, okay, so one parent is randomly selected. Okay, why? Because if we consider this one, one parent must be selected. Okay, so if remember that this is CK is BI blah blah blah. Okay, so here I write here CKE BI plus blah blah blah. Okay, so if n is 1, if n is 1, that means here must be B1, right? Because here we have CKE BI plus blah 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 blah. Okay, this formula. So now if n is 1, that means you get here B1. Okay, and yeah, we just follow the formulas. If it's B1, so we need to calculate E2, E3. Okay, yeah. And deltas. D here mean delta average. Okay, and then because IE1, so when we calculate delta average, we just consider delta 2 plus delta 3 over 2. So that is the reason here we just calculate delta 2 or D2. Okay, and then observe this. Okay, if we calculate delta 2, so we need to skip to B2. We need to skip to B2. Now, if you observe this one, we cannot see B2. Okay, and then when we calculate D3, we need to skip what? We need to skip B3. Okay, so here you can see no B3, and then yeah, and here this is the central point parent. Okay, so if n is 2, that means we have CKE B2 plus blah blah blah. Okay, B2. Here's B2. Here B2, so here is E1 and E3. So if now I E2, you can get delta average is delta 1 plus delta 3 over 2. Okay, here. Delta 1. This A, delta 3. Okay, you can calculate average. Here A, delta average. Okay, yeah. Okay, yeah. And if n is 3, that means CKEB3 plus blah blah blah. Okay, so we need to calculate delta average A, delta 1 plus delta 2 over 3. So we need to calculate delta 1, delta 2, and delta average. Okay, like this B3. And finish. After that, you can draw this distribution of children. Okay, so any questions so far? Okay, good. So for now, we go to the mutation operators. Okay, mutation operator. So we have uniform mutation. Okay, yeah, and yeah, we just apply the formula. Okay, yeah. So the uniform mutation is the simplest mutation approach. Yeah, and we just pick up for one parent B1, and we calculate C1. So I random. Okay, delta is correlation factors. Okay, yeah. Okay, so you can get mutation. We have normal mutation. Okay, and we have the combine. That means simulated binary mutation. Simulated binary mutation. Okay, so here, if Vmax means, yeah, we also mentioned about Vmax. Vmax mean upper boundaries. We mean is a lower boundary, so it depends on the random number. If the random number is less than or equal to BB, we get the children from this one. From this one. So if otherwise the random number is higher than probability binary mutation, okay, we calculate children from this one. Okay, remember that V mean and V max mean lower boundaries and upper boundaries of the solution. Okay, LB and UB. Okay, so yeah, you need to practice MATLAB, but got at home. Otherwise, you know, yeah, very difficult for you to understand the pseudocode. Okay, the theory. Yeah. Okay, so now we have example. So here we set up for binary probabilities is 0.5. So if random number less than, right, less than binary probabilities, we apply the formula here, you know, 1 minus blah blah V max minus P1. Okay, V max, this is V mean. Okay, so of course we need to set up low boundary and upper boundary here. Okay, and then you can see the distribution of the solutions. Okay, now for practice, now please open MATLAB. Now you have 5 minutes. Try to follow step by step. Okay, to use real parameter GIs. Real parameter GIs. Okay, this, yeah. Remember, this is maximize. We are going to find the optimal solution. Okay, to maximize objective function. Remember, now maximize the objective function, not minimize. You know, not minimize objective function. Okay, so look at this objective function. Okay, how many dimensions we have? 2, because we have x1 and x2. So every solution we have 2 dimensions, x1 and x2. Okay, and they also give us the result. Okay, the cost function has 3 maximums and 1 global maximization is actually is here. You know, x1 must be 0 and x2 must be 1.5. Okay, 1.5. So this is the best solution we have. We can get this result, right? Okay, 1.5. Yes. Okay. So for now, we follow slide 81. Okay, 82, 83, 84, 85. Okay, to get the result. Okay, so remember, if we use GA, we have some function, right? Some function. So now we have the main program. We have the main program right here. Okay, main program. Okay. For example, we set up the objective function here, the boundary, because we have x1 and x2. So we have the boundaries of x1 is minus 3 and 3. The boundary of x2 is also minus 3 and 3. Yeah, we know this format, right? And then you can get the function objective function. Okay, so we set up this population size. Okay, so that means we have n is 20. Okay, we have every population we have x1, right? x2, blah blah blah, to x20. Okay, we have 20 solution in the population. Okay, the maximum number of generations is 300. Okay, we have crossover probabilities is 0.95 and mutation probability is 0.05. And I also explained to you why crossover operator is higher and mutation operator is lower. Yeah, we discussed before. Okay, so from now this one just draw a surface. Okay, and then section one does mean we need to generate the first population. Okay, how many solutions we have? 20. Okay, yeah, so n is 20. N is 20. Okay, so that means for solution, right? For solution we have yeah, for our solution we have x1, right? X1. So we have x1, this solution, okay, to x20. Okay, so every solution we have two dimensions, right? Two dimensions. We have x1 1 and x1 2. Here you get x21 and x22. Okay, yeah, because every solution we have two dimensions. Okay, yeah, so that means we have 20. Okay, 20 rows and 2 columns, right? The first column and the second column. The first column for the first dimension, and the second column for is for the second dimension. And then we have, so finally you have 20 rows and 2 columns. Okay, yeah. Okay, so for section 2, selection IM. Okay, we know, right? Selection IM, selection, yeah, selection operators. Now section 3 is crossover. Section 4, mutation, right? Okay, and then yeah, and this is a function. Okay, this is a function for selection. Okay, selection, yeah. And remember, we use XPX. We use XPX. Okay, XPX crossover, simulated binaries crossovers. Okay, crossovers is a function. Okay, we have mutation. Then you get the result. Okay, now 5 minutes, do it. Maybe 5 or 10 minutes. Okay, and now we have 1:55, and yeah, I hope you can finish 2:05 a.m. b.m. Okay, do it 10 minutes. So if you have any questions, ask Mr. Okay, after 5 or 10 minutes, I will run to my code and yeah, to let you understand more. Okay, 10 minutes now, please. Remember, we have main program, and we also have such function. Okay. Or you can go to the textbooks, and then you can yeah, I also upload the textbooks, okay, into which you Moodle, and then you can just follow this one. Yeah, follow this one. Just copy this one. Okay, this is the main set function here. It's the main set function. Actually, this is the main program, and we have a set function here. Okay, yeah, a set function. This is a function selection. Yeah, this is a function selection, right? So we have selection. Okay, this is main program, right? Main program here. We have the first set function, where the second set function will be here, crossover. Okay, and next set function will be mutate. Yeah. Okay. So now we have mutation. We have crossover. We have selection. Okay. We have short. Okay. Short. Okay. And yeah, finish. Okay. And do it, please. And here I can open my code. Let me see. This is okay. We have real GIE. Okay, real GIE, and you can see the set function, right? The set function selection. Okay, so we need selection here. Okay, what else? Mutation, and crossover. Okay, so we have three set function. Okay, and this is GA. So if I can run it. Okay, but of course you need to do it for yourself. Yeah, maximums. Okay, should be here, and now you can check the results. Results will be here. So I think we have some problem. Let me check. Okay, maybe. Yeah, just do it for yourself first. Over GD. Okay, yeah. We have some figures. Figure 1, figure 2, here figure 3, figure 3. Okay, figure 3. Okay. Hmm. Okay, so we need to say is hold on. Hold on, so you can see. Let me check. Okay, yeah, correct. Okay, do this please. Okay, so for time off. So for now, I will I will guide you how to make the pyramid. Okay, so now first of all, we come back here. This is the main program, right? The main program. So for the main program, okay. So now we step by step. Okay, check it. So we need to set up the objective function. Okay, how many dimensions? We have two, right? We have x1, maybe bigger a little bit. So we have x1 and x2. So if we come back to the MATLAB code, so we have x1 is x, right? x1 is x, and y x2 is y. Okay, this is x1, and this one is x2. Okay, yeah. And then we set up the lower boundary and the upper boundary. Okay, so here set up lower boundary and upper boundary for each variable. It's variable, right? How many variables we have? Two, right? Variables, or we say dimension. It's dimension. Yes. Okay, so and then you can so this is the objective function f. Objective function f. Okay, f. After that, we set up the population size is 20. Maximum generation is 300. Okay, so and the 20s. What does this mean in 20? That mean we have a population, right? We have the population of 20 solution. Okay. Crossover probabilities and the mutation probability. Okay, now and this one just indicates the figure. Okay, some figure. Okay, yeah, we have some figures here. Okay, yeah. Okay, so we generate the first population. Okay, so we can get x range and y range. X range is range 2 minus range 1. This is range 2. This is range, okay, this is range 1, range 2, range 3, range 4. Okay, so you study this one many times. Okay, so you can get x range and y range. Okay, so we can generate how many solution? We have 20 solution. Okay, and the 20s. Okay, yeah, we generate random 20 first element, and here 22nd element. Okay, so up to now we can get a matrix, right, of solution with 20 rows and 2 columns. How can we know now? Look, we can check. Okay, so here you can see this is the workspace. So we can see, okay, xn we have 20 and 1, and yn we have 20 and 1. So if we combine, you get 20 rows and 2 columns. Okay, yeah. Continue. Okay, so for now we start the optimization process. Okay, so this one just determines exact ends. What does it mean? Exact ends. Exact ends mean fixed values. Exact ends. Remember, exact ends is a fixed values. Sometimes, yeah, I mentioned to use many times. We say fixed values, or we say a values of objective function. Right? Okay. Then Now we go to okay, selection. Okay. Yeah, you know, from here to here, yeah, this is the loop. This is a loop for from slide 38, right? Slide yeah, a line 38 to the line 83. This one for the optimization process. Okay, so here we can get what? Here we can get some selection methods. Here is selection methods. Selection. Yeah, selection. Yeah. What does this mean, selection? You need to, yeah, this is set function, right? This is a set function of selection operator. Yes. Okay. So here, this is selection. Okay. Yeah. And you should remember, because we determine the maximum values of the objective function. Look, look, maximize. So here we must use ascent. So if we determine the minimum, we should use what? Use the attribute of descent. Okay. So that means you delete ascent, you use descent like this. Okay. Like this. Okay. We use descent. Okay. Yeah. So what does this mean? FB? FB mean the objective, objective function value. Okay. Yeah. So E mean the index. Okay. Yeah. So if we use DI, okay, and this is the matrix of fixed values. Okay. So we can know FB, right? FB. So we have FB is a matrix with 20 rows and 20 rows and one column. Okay, because we have 20 solutions, so we have 20 fitness values. Okay, you can double check FB here. Where's FB? Where's FB? FB means Zn, you know, look here. We have 20 rows and one columns. Okay, FB means Zn, because this is a function. Okay, so for the main program, this is Zn. So for this function, Zn is FB. Okay, so we can get the result. The result is D. Okay, yeah, vector D. Okay. Yeah, so for up to here, you can get the matrix of objective function values. Okay, when we make selection. Okay, so here we say this is the results. Yeah, after finishing these selection operations. Okay. Yeah. So after that, we can apply the roulette wheel process. Okay. They calculate the probability for every fitness values. Okay. Yeah, here you can get a cumulative probabilities. Okay, here. Yeah. And you have random. Okay, so if these cumulatives, cumulative probability is higher than or equal to random. That means we rec this means stop. Okay. Yeah, and then we can get the best. We can get the best. We can get the best objective function. Okay. Fitness. Sorry, objective function values or fitness values. Okay. Yeah. So we can guess what's the best solution. Okay. So I summarize for you. So here, so step 1, we need to sort the objective function values. Okay. Step 2. Okay, select the best solution. Okay. Yeah. So here, up to now, you can guess the best solution. Okay. Yeah. Yeah. So IE means the element selected. So IE means E here. Okay. So this is the first elements. This is the first elements. Elements of the best solution of the selected solution. Okay, or the first dimension, the first element of the first dimensions. Okay, and we have this one. This is the second. Yes. Okay. Yeah. So we finish selections. Okay, our fitness evaluation. Now we come to the crossover. Okay, crossover from here to here. This is crossover. Okay, yeah, 4 to ends. Okay, so this one is crossover operation, right? Crossover operator process. Okay, so and what kind of crossover operator they use? They use SPX. Okay, SPX. Okay, so using using SPX. SPX. Okay, where's SPX? Okay, we need to come back. So the theory about SPX. SPX here. Okay, this is the ideas of SPX. We need to choose two parents, right? Two parents. Okay, to generate two children, C1 and C2. From B1 to B2 to generate C1 and C2. Okay, we need to determine NC. Okay, and we can calculate beta. After you get beta, you get C1 and C2 like this. Okay, so come back here. We need to randomly select B1 and B2. But how many solution in the population we have? 20. Okay, so parent 1 and parent 2 are selected from a population, right? From a populations of 20 solution, right? Okay, so that is the reason here. Okay, so next one is 1 to 2 to n. Okay, of course we know n is 20. Okay, yeah. So now if BC is 100, BC, what is BC? BC mean the crossover what? Crossover probability, right? Here, BC. Crossover probability. So if BC hadn't range random, okay, random, we can choose crossover RE. Crossover RE is here. Okay, rush over A. And remember, we are using what? XBX. XBX. Okay, so we randomly choose NC, right? NC. Okay, so we choose NC is 1. We choose NC is 1 and RE random. Random. Okay. So A and B mean the parents, right? So here we can say A and B for parent 1 and parent 2, and C and D for children C1 and C2. Okay, so of course we have homework. Okay, so for the homework today, we need to use another crossover operators, maybe BLX answer, maybe UNDX, maybe it's BCX, and of course we need to submit the homework. Okay, on time. Okay, maybe I will set up the homework will be 15. Let me check now. So 15th. Okay, 15 December 2025. Okay, you can use another crossover operator like BLX answer, UNDX, and BCX. Okay. Yeah, of course you can use ChatGPT. Okay, to ask them about UNDX, blah blah in MATLAB code. Okay. Yeah, to finish. Yeah, you can use. Yeah, you can ask any AI platforms you like. Okay, I don't care. I just care about how can you get the result, and you compare the results of BLX and for UNDX BCX with SPX. Okay, which one is the better? Which one is better? Okay, that's enough. Okay, yeah. Any questions so far? Tom, are there any questions for the class? Hello, TA. Are there any questions so far? Okay, good. So for now, okay, so if we apply XBX, okay, if we apply XBX, okay, next step, we need to compare random numbers is lower than 0.5 or higher than 0.5. So here is this one, and we can calculate mu. This is mu. Mu or beta, you know the same, you know, beta, okay. Yeah, 2R, blah, blah, blah. Okay, so that means milk like beta. Otherwise, we can write this one. And then now, generation of individual for each dimension. Okay, so how many children we need? 2 children, right? C1 and C2. And every children, okay, every children, for example, C1, okay, we have 2 elements, right? Because every solution we have 2 dimensions. So for example, children 1, we should have C1x and C1y, 2 elements, okay? C1x and C1y. And for the second children, C2. So we have the first element C2x and C2y. Okay? C2y. Yeah. Okay, so now we can get some. So C1x and C1 is for C. Here we say C, we say D, right? We say D, C and D, C and D. Okay, C and D. So now we just apply the formula, right? C1 is 0.5 1 blood beta, blah blah, like this. Okay, 1 blood mu or beta. Okay, so we can update for the first element, for the second element of C1 of C, and here for so actually here I say D for easy, right? D and D. Okay, D and D. Here or here I just say Cx and Cy, dx and dy. Okay. Yeah, so here we have Cx and Cy. Okay, then dx and dy. Okay, dx and dy. Okay, and now you can get here Cx. Okay, Cx for the first element, right, of C, and Cy is the second element of C. Okay, so D1 is dx and D2 is dy. Okay, yeah, okay. Yeah, for easy, you know. So now you can understand the first element, right? The first element of C. Okay. And this is the second element of C. Okay. Similarly, this is the first element of the children D. And this is the second element of D. Okay. Yeah. So now you get children. Okay. Children. So now you can check C and C1 and C and D here. You can see C and D. C and D later on, right? Okay. Yeah. So now we get crossover. This is the result of crossover. Okay. So otherwise we keep. Okay. Otherwise we keep. So if this condition is satisfied, we come to crossover. Otherwise, the parents remain. The parent remain. That means MB, okay, MB, B1 is NBZ1. Okay, yeah. Okay, finish. And then mutation. This is mutation. Mutation. Okay, this is crossover. So this is mutation. Okay, come here. It's mutation operators process. Okay, yeah, you need to open MATLAB software and okay, do with me. Okay, now look, if BM is hidden range, okay, we come to the, yeah, we keep it. Sorry, we come to we set up mu1 and mu2. Okay, normal mutation. Okay, and then we come to mutate. This is mutate. Okay. And we are using normal permutation. Okay, we set up okay, I. What does this mean? I mean mu1 and mu2. Okay, we have two parents, mu1 and mu2. Mu1 is here, mu2 is here. Okay, and then we make mutation. Okay, so for mutation we apply two-dimension mutation. Okay, so we set up sigma is okay here. Maybe here we come to mutation. We come to normal mutation. Here, normal mutation. Okay, normal mutation. Okay, so we have parents plus the normal distribution with mu is 0 and sigma. Okay, so now we set up sigmas. Set off the standard deviation of normal distribution. Okay, and we set up the low boundary and upper boundary. Okay, yeah, and then we can make the mutation, you know. So the first element plus range n times sigma. Look here. Okay, so this term in the MATLAB is range n. Okay, n 0 sigma. That means range n times sigma. Okay, or you say, yeah, right here, range n times sigma mean normal 0 and sigma. sigma square here. Sigma, sorry, sigmas. Okay, yeah. So we can update for the first element, for the second element. Okay, and then you add into a new. Okay, what does this mean? A new mean the new solution. Okay, the new solution after we implement the mutation. Okay, and then after that we need to check the lower boundary and upper boundary. Okay, so if the first element, if any element is higher than upper boundary, we need to set up boundary, active boundary. So if the element less than lower boundary, we need to set up a lower boundary. Okay, so you make sure the new solution must be in the range of lower boundary and upper boundary. Okay. Or I can type something here. If a new, okay, any columns and any rows and the columns, okay, is outside of upper boundary, okay, and then we set up to be equal the upper boundary. Okay, so here if any element is outside, or we can say higher, okay, sorry, is higher and not outside, higher, okay, and here is lower than, okay, lower than the, we set up equal to low boundary. Okay, this is low boundary. Okay, yes. Okay, so finish. Okay, so for your homework, okay, I will ask you to use simulated binary mutation. Okay, so I copy here, and for the homework, for your homework, okay, please use the the simulated. Okay, yeah, okay, yeah, we don't use normal. Now we use normal, right? Now we use normal, right? We use normal, but for your homework, you should use, okay, for your homework, you should use simulated binary mutation here. Yeah, okay, you need to based on these formulas, okay, and yeah, make the program. Okay, yeah, so we finish, and now we just update xn and yn, okay, and then we calculate the objective function. Okay, we calculate it here, the main program. Okay, we come to the main program. Here, where is the main program? Here, update xn and yn. Okay, right? Yeah, xn and yn. Okay, so here xn and yn. Yeah. Okay, and then you can plot xn and yn, the final result here. But x and yn draw now horn on, horn off. Okay, if you see horn on, you can see if it's horn on, you can see yeah, you can see the history of generation, of solutions, of iterations. Okay, yeah, and then you can plot the objective function. Okay, objective function versus, okay, here, I mean, we plot the objective function versus the number of iteration. Okay, objective function values, or we say fixed values. Okay, versus number of iteration. Okay, yeah, so we just modify some code here. Okay. So any questions so far? Okay, so now you can run it. Yeah, so you can see, yeah, we have yeah, you can see, yeah, after some, yeah, you can say after some, yeah, because we have we're looking for the maximizations of the objective function. So here, this is correct, this is correct. Okay. And then you can see the result, after some, after 50, maybe 50 iteration, you can get the maximum objective function value here. 8.09, and then you can check the answers. This is 8.09. Let me see the results. Yeah, the maximum, right? 8.09, and the solution, this is 0 and 1.5. Okay, now check. So we can guess xn and yn. Okay, so xn is yeah, we cannot get exactly 0, but now it's minus 0, 0, 0, 87. That's okay. And how about yn? Yn, yeah, you cannot guess exactly, it's 1.5 because this is the idealized solution. Okay, but you can get 1.5311. Okay, yeah, so that's okay. Okay, yeah, so now you have 5 minutes. Try to correct your code, okay, and run it. Okay, 5 minutes now, and if you don't understand, hesitate. Okay, and if you would like to see my code, okay, just let me know. I will upload. Okay, my code into VG Moodle. Okay, so now you have 5 minutes. Try to correct it and run your code. Okay, yeah, please do it. So, are there any questions, Miss Tâm? Any questions so far? Em đi kiểm tra giùm thầy coi có bạn nào làm không được không? Đi đảo một vòng coi có bạn nào làm không được không? Okay. Bạn nào làm em điểm bạn nào là ba bạn làm đúng đầu tiên được cộng mỗi bạn là 2%. Bạn nào làm đúng thì nói các bạn đưa tay lên rồi em kiểm tra thì được cộng đúng kết quả thì được cộng 2%. So we have homework, right? So for the homework, let me see the homework. Okay. So for now, we have the homework of lecture 2. Okay, so you need to use B Lx and for un dx and bcx, right? bcx here. Homework. Okay. Yeah. BLX, UNDX, BCX. Okay. Yeah. For the crossover operators. Okay. This is first A. B. Okay. Use binary, simulated binary. Yeah. Simulated binary mutation. Okay. Here. Binary mutation. SBX. Okay. SBX. Okay. For the mutation. For the mutation operators. Okay. Operators. Okay. Yeah. Okay. In the real GA. Okay, in the real GA. Okay, we can keep the objective function. Here, we can keep the objective function like this. Okay, keep the objective function. And try to use different methods, different rush over operators and mutation operator. Okay, yeah, and then compare the simulation results. Compare the simulation results between BLX and for UNDX, BCX. right? BCX and what? As XBX, right? XBX here. And XBX. So this one is not XBX, this one is XBM. Okay, simulated binary mutation. Okay, a month. Okay, and answer to me, what's the best operators? The best operator in this case. Okay, and this question D, you need to compare the simulation result among a normal mutation and what else, and SBM, and answers. What's the best mutation operators in this case? Okay, yeah. And so for the answers, for your answers, okay, for your answers, you need to submit MATLAB file, MATLAB code, okay, MATLAB code or MATLAB files, okay, yeah. For question A and question B, okay, you need to submit the work file about your simulation result. That means C and D. C and D. Okay. Is it clear for you? Yeah. So for the work file, yeah, you need to add some figures. Some figures, okay, yeah, about your simulation. Okay, so here, look, I would like to ask you to compare. Okay, so how can we compare? Okay, so to answer these questions, you need to draw the thickness value, right? This is the thickness values. The thickness values, or we say objective function values. And this one is what? This one is K. What does this mean, K? Iteration. Iteration. So, of course, if we would like to figure out this maximization, okay, max objective function, okay, so after some times we can get the curves like this, okay, to this one for SPX, okay, and we use another curve, okay, so here, yeah, like this, okay, to this one for BLXN first, for example, you know, and for you know, UNDX like this, okay, UNDX, and we have the last one, this is BCX like this, okay, yeah, and then we say that BCX is better than the others, okay, yeah. So you should think about how can you draw the objective functions values versus the iteration, okay, in the same, okay, in the same figures, in the same figures. Very easy, you know. Okay, you need to export. You need to export the data from MATLAB. Okay, so we have data 1 for UNDX, data 2, data 3, data 4, and then you can use Excel to draw the data here in the same figure, or you can use MATLAB and then you can draw this one. Okay, yeah. And similarly, we have question D. So for question D, of course, this is objective function, objective values, objective function values, and this one is K. Okay, so maximization, right? So we get here for normal mutation. Okay, and we get another curse maybe here, yeah, for XBM. Okay, simulated binary mutation, right? Simulated binary mutation. Okay, yeah. So for the for the final report of the course project, you also do it. Okay, you should do it. Okay, so very easy, you know, very easy. So I will let you know how to export the data. Okay, for example here, for example here, you can see okay, so when you run to the code, okay, you can get the data. Okay, data. So data, it means you can draw the objective function, right? Objective function versus iteration. Okay, or I just type here. So we have a title. Okay, is the number of iteration. Okay, and we have y title for the fixed values. Yes. Okay. Yeah. Maybe I don't remember the format, and I need to check have X title. Okay. Wait, I need to check X label or X titles. Okay. Oh, sorry, wrong. X label. X label. Okay. Sorry. Okay. And Y label. Let me check. Okay. Yeah. Save it. Run it. Okay. Let me check. Okay, so for when we finish the running, yeah, you can get these objective function values of fixed values versus the number of iterations. Okay, yeah, we need to wait some minutes, yeah, to get the final result. Wait sometimes. Hey, cannot see. Maybe. Oh, well, we have some problems. Okay, X label. Some problem, right? Anyways, you need to check for yourself. Okay. Oh, wrong. Okay, label. Okay, maybe someone remind me, or TA remind me because I have wrong. Okay, anyway, yeah. Okay, so for now we have data I. Okay, data I see here. Data. Okay, so we need to export this data. Okay, so you can yeah, you can copy and then you pass into Excel file. Okay, or we can use export. Okay, or you can use ChatGPT to add how to export the data from MATLAB. Okay, they can give you some import or export data. Okay, here let me check. Okay, for long times I haven't used it. Okay, yeah, export. Okay, so here we can use, let me see. Mm, yes. Okay. Yeah. Study for yourself, or you just copy from the workspace. Okay. Uh, yeah, you just copy from the workspace here. Okay, data. Yeah. Just okay. Just copy or cell A's with mm, anyway. So you study for yourself. Okay, or the copies. Okay. So if you double click here, you can see we have 300 iteration, 300 iterations. So we have 300 values. Okay. Yeah. Okay. Yeah. And then you should modify. You modify um, some crossover here. Okay. Some crossover operator here. Okay. BLX or UNDX. You can get different data. And then you can add into the Excel, and then you can draw this the curve like this. Okay. Yeah. So I hope you enjoy it. And this is the uh, this is the homework of lecture 2. Okay. Now we finish lecture 2. Okay. We take a break. Okay. Oh, sorry. I need to tell you about minimizations. Okay. So here, this one for let me show Ace. Okay. And this one for maximization. So now I would like to figure out the minimization of objective function. Okay. So here cell Ace, you mean. Okay. So if we would like to find mean, where is mean? Mean here, right? Mean is here. Minus 6.3 blah blah blah. Okay. Yeah, we are looking for the mean objective function values. Okay. That means we would like to determine the optimal solution. Okay, optimal solution to minimize the objective function. So so we need to modify a little bit. So we need to modify selection, right? Selection. Now we use descent. Okay, we use descent. Yes, descent. And what else? What else? Or I need to sell A's. Okay, sell A's. I am here. I am mean. Okay, I am mean. Okay, and then you can get here. You know the name of the file and the name of the suspension should be the same. So this is mean. Okay, this is mean, and I modify here. This one should be mean. Where is mean? Here. Selection will be. Selection will be. Let me check where selection here. Okay, so I will use mean, right? Mean. Yeah, we would like to find mean. Okay, yeah. To find the mean objective function values. Yeah. Okay. So it. Let me check this descent, right? And what else? That's all I think. Let me check. Yes. Okay. Run it. Oh, we need to stop. Anyway, stop. I need to delete. Okay, delete. And then, yeah. Okay, you can see. Okay, yeah, you can get the minimization of objective function. I will, yeah, we need to wait some time. Okay, yeah. So you can get minus 6 boys, blah, 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 blah. Okay, yeah. I'm sorry because I forgot to delete. So maybe I run again. And now I just limit the number of iteration. Now it's 300. So now I just use 100 for quickly. Okay, so run it. Okay, yeah, you can see this is, you can see here, after sometimes, yeah, yeah, you can get minus 6, minus, minus 6 boy 5, and actually here must be, yeah, minus 6.3, blah, blah. Okay, so yeah, finish. So we can apply GI to determine the minimization of objective function and maximization of objective functions. Okay, it depends on different applications. Okay, any questions so far? Okay, so now we time break and we'll come back at 3:15. Okay, 3:15. Okay, I'm coming back. And Tom, can you hear me? Okay. So now we go to the next lectures, lecture 3. We discuss about evolutionary strategies. Yes. Okay, and I also upload. Let me see. Okay, here I also upload the homework. Oh, the homework of lecture 2, part 2. Okay, sorry, some typing here. Okay, so yes, and I also upload lecture 3. Okay, well, yeah, lecture 3 we have two parts, part 1 and part 2. Okay, and now we discuss lecture 3, part 1. Okay, and remember you need to submit your homework on time. Okay, so we go to lecture 3. Yeah, we study another optimization methods, that is evolutionary strategies. Okay, so so this optimization method is very common. Okay, and I think it's easy for you to understand. Okay, so we go to the introduction of ES. Okay, evolutionary strategies. Okay, so when we apply the optimization methods, of course, we would like to determine the optimal solution. Okay, the optimal solution, the better solution, the best solution to maximize the objective function or minimize the objective function. Okay, so to do that, we need to consider a selection. Sorry. We need to consider selection. Hey, what problem? Hey, right? Yeah, we need to consider selection operation. Okay, crossover operation and then mutation. Okay, so if we use J, we focus on crossover, okay, and mutation and selection. But we have another methods. They just focus on some of them. For example, for ES, okay, evolutionary strategies, they focus on mutation. Here, mutation. Yeah. So the random solution were modified and re-evaluated to verify. So when we do the mutation, okay, you can get the solution. Okay, so you need to evaluate the new solution or the new children that will be better than the parents or not. Okay, so if the mutated solution was is not improved, okay, it's not improved, okay, we need to discard. Okay, you need to skip the mutated solution. Okay, so anyway, if you would like to get the new solution, yeah, you should think about applying the mutation. Okay, the mutation. So ES will focus on the mutation operator. Okay. So species are mutated to improve and adapt to changes in the evolutionary process. Okay, so the solution could be improved. Okay, the solution could be improved if they were mutated to evolve. Okay, yeah, and for evolutionary strategies, we have many variants. Okay, we have many versions. Okay, yeah, and the basic one on this, the simplest one is 1 plus 1 ES. 1 plus 1s, that means we only need one parents and then we can generate one children. Okay, one children. We say 1 plus 1 is. If the offspring was better than the parent solution, the offspring of the children were selected to be a father, and the original fathers will be discarded. Okay, I mean skip it. Otherwise, the offspring was discarded. Okay, so it depends on the comparison, the fitness values between the parents and the offspring. If the offspring is better, we delete the parent. Otherwise, we delete the offspring and we keep the parent. Okay, yeah. So the original algorithms 1 plus 1 is. That means one parent, right? And one children. Okay. Was modified by these professors, okay, 2002. Yeah. And after that, we have some modification of evolution strategies algorithm. Okay, so now, yeah, so for lecture 3, we will study 1 plus 1 is. Okay. We study 1 plus 1 is. This is the basic one. And then we study adaptive 1 plus 1 is. Okay, mu plus 1 is, mu plus lambda is, mu lambda. Okay, and mu alpha lambda beta. Okay, adaptive mu plus lambda. We have mu plus lambda and adaptive mu plus lambda and adaptive mu lambda. Okay, yeah. So we study many modifications of ES, of the basics ES. Now we go to the easiest one, 1 plus 1 ES. So for 1 plus 1 ES is very easy. Okay, you just need one parents. Yeah, you just need one parents, and then we generate one solution, one children. Okay, so we need XP, the parent, we generate X our mean offspring. Okay, yeah. If the new particle X0 is better than the parent XP, then X0 will take place of XP. That means X0, yeah, input to XP. Okay, otherwise X0 will be discarded. Okay, yeah. Now we go to details. Okay, step 1. We need to make initialization of the solutions. Okay, yeah, and yeah, you are very familiar with this one, right? We have solution. How many dimension? D dimension from 1 to D. Okay, so that means every solution we have x1, x2, blah 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 to xd, D dimension. And we have x1, x2, blah blah blah, xd should be higher than or equal to lower boundary LB and less than or equal upper boundary. Okay, yeah, we need to determine the search space. Okay, for every element, this is element. Why I know this one is element? Because this is italic. Italics means element, and if we have arrow, that means it's a vector. Okay, yeah. So if we use this format, you can you can randomly generate the solution at the beginning. Okay. Yes. Okay. Now, how can we update? How can we? I mean, how can we generate the new solution. Okay, the new upstream. Yeah. So to generate the new solution of upstream, we need to consider a standard deviation. A standard deviation. Okay. Because to get upstream, this is x0 is xb plus rho. Okay, plus rho. What does this mean? Rho mean mutation vector. Mutation vectors. Okay. Yeah. So to calculate rho's, you need to determine standard deviation. Okay. Yeah. So here, look. Number 2, step 2, mutation. Okay. Yeah. So when we finish the first step, initialization, you can get xb, right? And then you need to calculate mutation vectors. This is mutation vectors. Vectors. Okay. So the mutation vectors also has d dimension, rho 1 blah blah to rho d, and then if we apply the normal distribution, you can get rho. Okay, so if you see n0 sigma square, that means in MATLAB you need to use ren n time what? Time sigma, right? This is the command in the MATLAB, ren n times sigma, and you need to determine sigma how many. Okay, so normally sigma is 1, 2, or 3. Okay. Yeah. So now we can get mutation vectors. You take the sum of mutation vectors and the parents, you can get x0. Okay. Yeah. Okay. Or you can consider the covariance matrix. Okay, we have d dimensions. So this one we update for the first element, the second element x2, blah blah blah, and this one for xd. Okay, or you can say that xb, right? The parents we have x1, x2, blah 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 to xd. Okay, and we have mutation vectors. We have rho 1, rho 2, blah 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 to rho d. Okay, so if we take the sum xb and mutation vector, you can get x0, right? X0. So x0 is x1 plus rho 1, right? x2 plus rho 2, blah blah blah, xd plus rho d. Okay. Yeah. Yeah. Okay. So for example, here we have the objective function with two elements, two dimensions, x1 and x2. Okay. So you can get the 2D surface. Okay. And we would like to determine the maximization of objective functions here. Okay. So after some iteration, okay, you can get the best solution. Okay. Yeah. Step 3, selection. Okay, so step 1 is what? Step 1 is initialization. Okay, step 2, mutation. Okay, now step 3, selection. What does this mean, selection? That means we are considering that we choose x0 or we keep xb. Okay, if x0 is better than xb, we choose x0. Otherwise, we skip x0 and we keep the parent xb. Okay, so how can we implement the selection operation? We compare the fitness values. Okay, so if we have xb, we can calculate the fitness values of xb. We have x0, we calculate the fitness values of x0, and it depends on our purpose. If we would like to get maximization, okay, so xb for the next iteration is xbk if f what? Maximization, if fxbk higher than fx0k. So, and then here we get x0k. Okay, x0k. So if xbk, less than or equal to fx0k. Sorry, we have some information. Okay, because now I am staying in Taiwan, so we have some news. Okay, so maximization, yeah. Why? Because if this is higher, that means xb is better than x0. You need to choose xb for next iteration. Otherwise, if if the fitness of xb is less than the fitness values of x0, that means we need to keep x0 for next iteration. Okay, this is maximization. And now this one for minimization. Okay, minimization here. Okay, look for minimization. If fx0 less than fxb, this one is also for maximization. Sorry, maximization. So for minimization, okay. So for minimization, maybe right here. So xb k plus 1 e xbk. If fxbk less than fx0k, right? If less than, that means xb is better than x0. Then xbk plus 1 is x0k if fxbk higher than or equal to fx0k. Okay, yeah, the fitness value of x0 is lower than the fitness value of xb, and then we are looking for the minimization, so we can choose x0k. Okay, yeah. Any questions so far? Tom, are there any questions? Okay, so continue. Okay, so now we have this summarization. Okay, summarization of algorithms 1 plus 1 ES. Okay. So first of all, we need to randomly generate XB. Okay, and then we generate mutation vector row. Okay, after that we can get the upstrings x0, x0k. After that, we evaluate the objective function of fxb, k, and fx0 k. Okay, it depends on we are looking for maximization or minimization. Okay, and finally, okay, the most suitable individual is selected. Okay, so this process is repeated until our stop criterion is reached. Okay, that means if k is a k max, we get the maximum iteration. We can stop. Okay, so now this is the flow chart. Okay, start, we do the parameter calculations, initializations, evaluate the initial particle in the objective function. That means you can get xb0. Here you can get the fixed values of xb0, and then we go to the loop. Okay, this is the loop. Okay, we generate mutation vector row, right? We make mutation, that means x0 a xb plus row, right? And then we selection whether we choose xb or x0, and then we check the stop condition. If no, repeat. Okay, repeat. If yes, we stop. Okay. So for this is the pseudocode. Okay, how many steps we have? 8 steps. Okay. We need to set up lower boundary, upper boundary, dimension, the number of iteration, okay, Kmax, and variant, variance. According to variant, you can guess standard deviation. Okay. Yeah, we random generate XP. Okay, we evaluate fitness values of XP. This is fitness value of XP. Okay, we generate mutation vectors. Okay, you can use the command ran n times sigma. Sigma you determine here. Okay, yeah. So if you use this one, you can get mutation vector row. Okay, step 5, we generate the offstring. We generate the offstring. We evaluate the offstring. We evaluate the fitness values of upstream. We compare, right? Selection, we compare. So this one is maximize or minimization. Look, okay. So this is less than, then we get the minimization. Minimization. Why? Because if the fitness value of x0 less than the fitness value of xb, we choose x0. Okay, so this one is minimization. Okay. Yeah, and then we apply the new solution for next iteration k plus 1. Okay. Yeah. Verify stop condition. Okay. If this condition is satisfied, we stop. Otherwise, we update for the next iteration. Okay. Yeah. Now we have example. We have example. Look, in the examples, it's intended to minimize, minimize the objective function here. Okay, here how many dimensions we have, it depends on you. Okay, that means you design how many dimension we need. Okay, because here they just say xi. Okay, so normally dimension is 2, 3, 4, blah blah blah. Okay, and if we are considering this that is 2, you can get the global minimum of 0. Okay, as x1 is 0 and x2 is 0. We hope we can get the best solution. Okay, x with 0 and 0, right? Yeah. Now we have the code. Okay, we have the code. So yeah, this code. Okay, slide 20, 21, 23. Okay, and then you can get the result. So we hope we can get the objective function values like this. Okay, right? So here you can get x1 is 0 and x2 is 0 also. Okay, so now 5 minutes or maybe the 10 minutes, 5 minutes, I think that's enough. Okay, yeah, to run this MATLAB code, slide 20, 20, 21, and 23. Okay, so now we have 40, and then you finish at 3:45. Okay, you have 5 minutes now. Do it, please. Or if we go to the textbooks here, the textbook, okay, chapter 3, and we have the code will be the base 71. Okay, base 71. Okay, so do it. 5 minutes. Okay, time's off. So now we okay, yeah, we run the code. Okay, let me check. Okay, uh, I think this one just open it. Remember. So we have yeah, this is the code, right? Yeah. So now we step by step, so we should follow. Okay. So over here, um, okay, uh, dimension it too, and we need to set up, right? We need to set up a low boundary here. This is a low boundary. Okay, like this, low boundary, upper boundary. So this one is low boundary because we have two dimensions. So this is the lower boundary of the first dimension of the second dimension. So and upper boundary of the first dimension of second dimensions. Okay. So if we have n dimension, we can set up LBA low boundary of the first dimension, low boundary of the second dimension, low boundary blah blah blah, low boundary of the d dimension. Okay. And similarly, we have UB. We have upper boundary of the first dimension, upper boundary second dimension, blah blah blah, and upper boundaries of the d dimension. Okay. Yeah. K0 and the maximum number of iterations is 500, sigma into invariance, sigma square. Okay. So and then of course we can use this format to you can use this format to define the objective function. Okay, you can use add and the variable x. No, this is solution x, not variable, solution x, and 10 times d blah 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 like this. Okay, 10 times d blah blah blah. This one is x. This is so x here is solution. This solution, not dimension. Okay. Right? Yes. Yes. The sum of, yeah, okay, correct. So for XB, we initialize the population, okay, XB, E ran 1D times upper boundary minus lower boundary plus lower boundary. Okay, so here you can get what does this mean? Rank 1D. This is the matrix with 1 rows and D columns. Okay, so rank 1D, yeah, is the random matrix of 1 rows and D columns. D dimension doesn't mean D columns. Okay, yeah. Yeah, we evaluate the fixed values of XP. Okay, and then you draw these 3D surface. Okay, and now we go to the iteration process. Okay, if k is less than k max is what? K max is 500. Okay, and then we calculate row, right? We generate mutations, row. Okay, row. Yeah. E normal range. Okay, normal range 0, sigma, 1, and this. What does this mean, normal range? Okay, back here, I give you some suggestions. Okay, so normal range, do we generate the random array? Okay, from the normal distribution. Okay, so this one is mu, this one is sigma, this is 1 rows and D columns. Okay, yeah, that means we generate the mutation vectors with 1 rows, right? 1 row and the column. And the column. Of course, the D is what? D is 2, right? This is 2. This is 2 here. Okay. And yeah, this is random, right? Random. What does the random does mean? The row is 0, 0 and 1, right? Yeah. After that, we make the mutation. Okay, XB plus row, you can get X0. After that, we verify the search by limits. If the elements of the upstrings is less than low boundary, we need to set up X0 again, okay, or higher than upper boundary, we need to set up the low boundary, upper boundaries. Okay, so less than low boundary set up to be equal low boundary. Otherwise, if higher than upper boundary, set up to be equal to the upper boundary. Okay, we evaluate the fixed values of X0. Okay, yeah, and then yeah, we draw the particles XB and X0. Okay, yeah, yeah. So selection. Now selection. So here is for me generate, okay, mutation, and now this is selection. Yeah, selection. Selection. So this is minimization, right? This is minimization. Yeah. The purpose is to determine the minimizations of the objective function with the optimal solution. Okay. Yes. Okay. Then, if this condition is satisfied, we add X0 into XB for next iteration. Okay. Okay. Yeah, and we update the fixed values. We update the fixed values. Okay, so here we update the beta solution for next iteration. Okay. Yes. And then for every iteration, we store the fixed values. So after that, you can draw the curve of fixed values versus the number of iterations. Okay. So here, this is very important. Okay. We plot data. And then here we have X label for right X labels. How can I use X label? I forgot. Okay, have X label. Hey. Label. Oh, yeah, X labels, and yeah, we need to follow this one. Okay, name and values. Okay, for example, X label. Okay, and the population. Okay, so X labels. What? The number of iterations. Yeah. Then we have Y label, A, the fixed values, or the objection values. Okay, so on. Let me see. Okay, so it's yeah, run. Okay. So you can see, yeah. Okay, this is the best. This is the better solution. Okay, for each iteration. This is the pink. Okay, and the yellow for each iteration. Okay, yeah, they update. They will update the best solution after each iteration. So pink color for XB and yellow color for X0. Okay. Okay, we need to wait some minutes to finish the number of iterations. Of course, we cannot guess exactly 0, 0, like this one, at the global minimum of 0. Okay, that's mean the objective function is 0. The minimum objective function value is 0 at x1 is 0 and x2 is 0. But when you run, yeah, we cannot get exactly. Okay, x1 is 0 and x2 not 0. Maybe 0.0, blah, 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 1, 2, 3, blah, blah. Okay. Yes, okay. So this is this number of iteration, and this is the fixed values. And then you can get, yeah, I mentioned before, you cannot guess exactly 0, but okay, you can see, yeah, and the objective function values is not 0. We just guess 1.11. Okay, so that means 1 plus 1 is, okay, 1 plus 1 is not good. It's not good because we cannot guess the minimum objective function to be 0. We cannot. Okay, so we apply the variants, the update versions of ES. Maybe we use adaptives here. Okay, we can use adaptive 1 plus 1 and blah blah blah. Okay. Okay, so for now, we can modify. We can modify the number of dimensions. Okay, so here how many dimensions? 2. Okay, so now I modify. I wanted to get more dimension because here the objective function they give us is here, you know. Yeah, you can choose any dimension we want. Okay, so here maybe I shall as okay, and here okay, order this. Okay, so now I would like to get the dimension is 5. Okay, so that means we need to have 5 values of lower boundaries, right? 5 lower boundaries. Minus 5.12 minus 5. Of course, we can use ChatGPT to optimize, okay, the MATLAB code, okay. But now we don't have more time, so we just follow the basics MATLAB code here. Okay, yes, and 5.12. How many? 1, 2, 3, 4, 5. Okay, we have 5. And the maybe just 200. Okay, then let me check. Okay, are there any information we need to revise? Let me see. Okay, finish. I am afraid of we cannot draw the surface because now we have 5 dimensions. Maybe we have some problem here. Okay, yeah, here we only have 2. Yeah, so maybe we have some problem, you know. Yeah, this one just 2 dimension, you know, 2 dimension. Actually, we have 5 dimensions. So you just skip this one. It's incorrect. Okay, so now 5 dimension. Okay, we hope we can get 1 at 0. Okay. You're incorrect. Yeah, we cannot guess. But this is stupid. This is stupid methods. Okay, because yeah, we cannot get the correct answers. Maybe we need to double check whether we are wrong. Let me see. Change 1 to 5. That's it correct. That's it correct. Let me see. Because we have 5 dimensions, so we cannot observe. We cannot observe the figures of x base and x0, but the code is correct. Okay, I believe it. Okay, anyway, we can get more dimension to understand this 1 plus 1 is. Okay, now we stop the class today, and next week we have no class. Okay, we will have no class. Okay, let me check because I'm busy. Yeah, I'm busy the next week. Yeah, I'm busy next week. So next week we don't have the class. Okay, and Dr. Wong will cover. Okay, yeah, next week. Okay, Dr. Wong. Okay, because I borrow okay 2 class. Okay, from him. So now yeah, he will cover. Okay, yeah. So remember, we don't have the class of this course next week, but you need to submit your homework. Okay, and yeah, Dr. Hung will just use this course of smart building. Okay, is it clear for you? Yeah, and we will come back at 22 December, and 22 December is okay. We need to study more class. Okay, here and here, because totally we have 15 or no, totally we have 17 classes. Okay, so now 1 2 3 4 5 6, okay, 7 8 9 10 11 12 13 14 15 16 okay, anyways, yeah, okay, we do have more class of this course. Okay, any questions so far this time? So now we stop at the slide, uh, this slide 25, and yeah, see you next 2 weeks. Goodbye. Bye.